Hello, everybody. Hey, welcome. So today we're here for a special public talk before our normal astronomy night series, where we're going to be hearing from a few different cosmologists, John Groh, Clara Vergès, and what's it called? Julien Tang. And we're going to be hearing about the cosmic microwave background. We'll have about an hour of interesting science, and then we'll be going up to the 6th floor where you'll get to see the stars. Hopefully it stays clear, and do some stargazing. Awesome. Without further ado.
Well, thanks very much. So my name is John Groh. I'm a staff scientist at Lawrence Berkeley National Lab, just the hill. You probably all have seen the buildings. My colleagues, Clara and Julien, are going to follow me. I'm going to talk a little bit about what is the cosmic microwave background and what are some science that we are hoping to do in the near future and that we're currently doing as well. By using this as a tool to study the universe and some really cool physics. Clara is going to follow by talking about how we actually go about making those measurements. How do we make these telescopes? What is it like to do that? And Julien is going to talk a little bit about what it is like to actually perform that work, to be a scientist. And I should also mention, Juliet here is the Education and Public Outreach Manager in the University of Chicago, and also with our CMBS4 collaboration, who will be helping. We have some cool toys that, as long as you promise not to break them.
He said speak louder.
Can't hear you at all.
So, yeah.
Okay, I will do that. Thank you.
Thank you.
Let me know if I ever trail off, and just give me a heckle. Okay, and one thing I should also mention is that though the three of us here do work in Berkeley, about 100 scientists from mostly around the US, but also across the globe, including some here, have gathered to. We're planning the next generation millimeter wave observatory, and so I hope that if other of our colleagues are here and they choose to wear their name tags, maybe that will signify that they are open to being approached for questions or comments or anything like that. So hide your name tags if you don't want people to talk to you. So anyway, so we're going to talk about the cosmic microwave background. This is a map of it, but I'll get to what this means because it just looks like a jumble right now. So let me first start with changing the slide and giving a super lightning tour of what we know about the universe. And actually, can I get a really brief show of hands for who has attended, let's say, just an astronomy talk like this before? Okay, great. So hopefully there'll be something for everyone here. I will show a couple equations, but they're probably not necessary, and we'll also have some really cool pictures. So we know the universe is about 14 billion years old right now. That's today. It's filled with things like galaxies. And we know that the space in which these galaxies inhabit is a dynamic object. It's actually stretching and moving and growing. And for the last 4 billion years or so, the space itself has been expanding at an accelerating rate. So we'll get to more of that later. For most of cosmic history, and remember that's most of 14 billion years, we've had things like stars and galaxies around, and they've been slowly clumping into bigger and bigger structures, older galaxies, clusters of galaxies, filaments of clusters of galaxies, etc. But at some point, there were the first stars, and that was about 0.1 to 0.4 billion years after the Big Bang. At some point, before the first stars, there was the first light. Or at least the oldest light, I should say. And we think that was about a couple 100,000 years after the Big Bang. Sounds like a long time, but relative to 14 billion years, that's super young. Okay, so other really important thing about our universe is that most of it is filled with weird stuff. If you do a tally of the energy density in the universe, we are this little green sliver, about 5%. Technically, we call it baryonic matter because by mass, it's mostly baryons. That's just a fancy word for protons and neutrons. All the atoms that are in your body and in the ground and stuff. Two-thirds is this stuff called dark energy, which has actually been in the news recently. If you follow the New York Times or Scientific American, some of our colleagues at LBL just had a pretty cool result. But I'm not here to talk about that. But you can ask us about it if you want. And we don't really know what this is yet. We have some guesses. It could be this thing called a cosmological constant that dates back to Einstein. It could be something called quintessence, which sounds really fancy. It could be black holes, maybe. And then the last quarter is something called dark matter, which we think is stuff. It's like a matter. It's not an energy. But we don't know what it is quite exactly. It could be some kind of new particle. Could be primordial black holes. Or, if you look around online, you can supposedly buy dark matter for $19.99 a bottle. So I haven't bought one yet. But if any of you try it, let me know. So let me get back to the fabric of space. I was saying that space itself is expanding. And let me just say what I mean by that. It means that objects don't necessarily change their positions, but the space on which they sit is being stretched. So if you ever, you remember your middle school math class, where you have to compute the distance between two points in space. It's the square root of the sum of squares of the difference in coordinates. No worries if you forgot it. What happens in the universe at really, really large scales, cosmological scales, many, many light years away, is that distance formula is actually not totally true. But what is true is that it's the same thing, but you multiply it by this thing called a scale factor, this A of t. A is the scale factor. And this turns out to be a solution to Einstein's equations, which you can derive in a really rigorous manner. I don't have time for that. So you'll have to trust me. But A is a changing object that we can go measure. And in fact, the knowledge of what these components is helps us really determine how A has evolved over time and what the shape of the expansion of the universe has been. And specifically, it looks like this. So what I'm plotting here is that scale factor A. This is a logarithmic scale. So every tick is another multiple of 10. And the same thing on the x-axis is time. Every tick is another multiple of 10. So, most of cosmic history is just in this last little bit, because that's 10 billion years. And the scale factor has just been growing slowly, smoothly, in a nice little way. That means that the universe has just been expanding and expanding and expanding for all of the time that we know so far. And, we're at a really interesting point where it's actually starting to speed up in this kind of cool uptick. But that's another talk. And one important thing is that the more things have expanded, the more they've cooled. This happens with stars, or gas, if you've ever heard about people talking about this in other astronomy talks. Same thing with the universe. And so that means that even if most of space is a pretty cold place, it used to be that most of space was a super hot place. And that we'll get to what that means with the microwave background later. And now I'm making a bunch of wild claims. Why should you believe this? I definitely don't have time to give you the, this measurement in these, this year proved this and this other measurement here. But let me at least say that we know from multiple really different observables of the universe, they all kind of give the same picture. So one of them is measurements of how cosmic structure has evolved over time. This is actually a simulation, but it shows it better than a measurement. If you watch how galaxies have come together and clumped under the influence of gravity and pushed back out under the influence of things like stars and supernovae, the dynamics of that collapse can really tell you about what is collapsing. How does the gravity work? How much stuff is there? Because it goes slower or faster depending on what the ingredients are. Another main observable is we can just directly measure the expansion rate. We can use something called a standard candle. An example of which you may have heard about is a supernova. We know how bright it is and how far away they are, or at least the relationship between those. And you can map out basically the envelope of how much space is stretched and see kind of the average stretching rate. And then another really big one, which is what the three of us specialize in, is you can measure the oldest light in the universe, the afterglow of the hot Big Bang, or the cosmic microwave background. And so this is what it looks like. And again, I'm gonna walk through like why it looks like that. So if you remember, I showed you this plot about how the universe has been cooling over all of cosmic history. It used to be a really hot place. Now it's pretty cold, at least once you're in space. Here's an exception. And we know how physics works pretty well. We can heat things up on the ground. We can smash particles together, and we know very confidently that at around this temperature, which isn't super crazy, the sun is hotter. Neutral gases become ionized, and most of the universe is actually hydrogen gas. And what that means is that at colder temperatures or later times, most of the universe was a neutral, non-ionized hydrogen gas. A small caveat on that with reionization. For the sake of the story, that's mostly true. And before that, everything was an ionized plasma. And a final fact is that ionized plasmas, that means that the electrons are no longer bound to individual nuclei. And they are opaque to light. Photons just rattle around and they don't go very far and they don't travel in a straight line. But gases are opaque, are transparent. And so at this point in the history of the universe, about a couple 100,000 years after the Big Bang, about 14 billion years ago, all the photons that were rattling around got released. And that is the cosmic microwave background. It's been streaming towards us, and we're seeing this snapshot of the really, really infant baby universe if you look out with the right wavelengths today. So what does it look like? It looks like this. Actually really boring. It's the same everywhere. This is a map where I've kind of flattened a sphere onto, the projector here. And this was actually measured by an Hubble satellite, and it got someone in Berkeley a Nobel Prize at one point in history. And the intensity of this, which is just shown by the color, I don't have a color scale, tells you about how hot the universe was back then and how much space has stretched between then and now. But, if that was the end of the story, then we wouldn't really be here talking. It turns out that if you zoom in and you subtract off this average value, there's a whole bunch of information. And so this looks pretty complicated, right? So what we're looking at here is the color are the deviations in the intensity of the light. And then the little ticks are actually the polarization of the light, because light can be polarized as well. And it still maybe looks like random noise, but there's a lot of information in that noise.
Can I just ask, is the map distorted the way a normal 3D map is distorted? So I'm trying to think what the poles would be, or clearly it's a sphere, so everything's equal, but it's not looking like that. So it's actually distorted.
Great question. Yes, you can't. There's many ways to take a sphere and flatten it. You've maybe seen maps of the Earth that are rectangles, and some that look like an orange peel. And they all have their pros and cons. Like the orange peel one kind of preserves the area so that Greenland doesn't get super stretched. In the rectangle one, Russia's way too big. I believe that this is the mall-wide projection, which doesn't stretch things either at all, or at least not much, in a way that we like for looking at it and not getting confused as scientists.
It almost looks like there's poles. The poles, at least the vertical, are different from the horizontal ends.
So one thing that we do know about the universe is that it appears the same in every direction. So there actually is no preferred up and down or north and south. We do happen to plot it with one way pointing all the same way, mostly just because of the way that our galaxy is kind of flat and it's super convenient for us to define something as up and down.
So that's just arbitrary.
Yeah, if you were to plot it with different angular scales filtered out, it would probably look a little different. And I claim that any preferred direction that you see here is a trick of the eye. Yeah.
So that doesn't look uniform.
No, and this is not. So this is with the
You said
average
the universe is
subtracted off.
uniform.
I should be more clear. The statistical properties are uniform in every direction. So the average is very similar. But of course, yeah, we live on planets. This is the difference between you and me is we're pretty non-uniform creatures, right? So clearly that picture has to break down somewhere. And yeah, but on cosmic scale, so like billions of light years, everything actually still looks like a reasonable average soup. And on moderate scales, there's kind of like a nice noisy picture like this. And then on really small scales, yeah, you get planets and everything's really nonlinear and not very cosmological at that point.
But this is temperature. We're looking at temperature, right?
The temperature is the color. And
Yeah,
then the
so that's
ticks
what we're
are-
seeing right now. The different temperatures represented as color.
Yes, exactly.
So uniformity is not temperature, it's matter. When they say the universe is uniform, wherever you look at it, we're talking about matter, not temperature. Or is it everything?
Well, so the intensity of the radiation here, I'll get to this in a little bit, but just a sneak peek, tells you about the condition of how dense things were, how dense the matter was at this early time in the universe. So they are very related. At that time, about 14 billion years ago, of course, it's since been traveling to us for about 14 billion years, and there's a lot of matter in between that kind of distorts it a little bit. I'm actually not sure if I'm answering your question. Am I
Yeah,
getting it?
you are. You're-
Okay. So we'll have a ton of time for questions more later. I don't mind being interrupted. So if you do have more, like, just shout it out. But we do probably also have to like move along a little bit. So let's I don't know what I mean by that. Just keep asking. So let me say a little bit about give a feel for how we can interpret these maps. So this is a little cool applet that someone made. And we have theories of a relatively simple model of the universe that has fewer than 10 free parameters that actually describes things at large scales, and especially in the cosmic microwave background, quite well. And some of the main parameters are what are the energy ingredients into the universe. How much matter is there? That's this top bar. How much dark matter is there? The stuff that's not like protons and neutrons. That's this middle bar. And how much dark energy is there at the bottom? And this, most of the area is like, what would the cosmic microwave background look in a hypothetical universe with that distribution of stuff? And the top little right corner is what ours is. So let's say you don't believe me. You're like, hey, John, this dark matter stuff, I'm not buying it. This dark energy stuff, that's too weird. If we turn those knobs all the way down, crank up the matter all the way to 100%, it's super distinct from what we actually see. So we're quite confident that the cosmic microwave background, along with several other tracers of the universe, is telling us that there's weird stuff out there. And so let's go back to this presentation. Oh, that's unfortunate that it. Let me quickly fix that. Okay. Great. So yes.
Sorry, what was that? There was a little text box that said the universe is flat in that case. What causes that?
It's a great question. So that refers to the geometry of the Lorentzian manifold on which we define space-time. So basically, space is 3 dimensions. Time is a dimension because it's kind of changing. You can go back and forth. Well, we can't go back in time, but it is moving. There's a time coordinate. And at least our brains can kind of easily think about curving space. Take a sheet of paper and curve it. That could be something that has spatial curvature, we say. And it turns out in a 4-dimensional sense, it's a little bit hard to think about. The universe itself can be flat. It can be hyperbolically curved, or it can be elliptic, or it can be open. Closed, open, or flat are probably the easier ways to say it. And before we went and measured this stuff, we kind of thought it could be any of those. And it turns out it's flat, which is like right in between them in a special case. And one of those bars had to do with like, okay, you can vary that, but we sort of know that that's not the case these days. Yeah. It would be really cool if it wasn't the case, but it turns out it's flat, and that's sort of the boring gets
So
it.
you say cranking up the mass, you're saying if you projected what the inhomogeneities would be based on the mass inhomogeneities we know now, you'd project that's what the background would look like. It doesn't fit.
Those parameters are actually like how much total mass is in the universe, sort of in an integrated sense, not necessarily. unrelated to the amplitude of the inhomogeneities, just how much mass do you put in here if you're, the god turning the knob, saying I'm cooking a universe in my pot.
The background, the inhomogeneities in the background changed when you did that.
They did. And this is a perfect lead in, because why does the amount of mass affect that? It turns out that if you have more or less mass in baryonic matter, which couples to light and has like electromagnetic interactions, as opposed to dark matter, which only follows gravity as far as we've at least been able to detect so far, those are two very different beasts. The baryonic matter will like oscillate pretty, there's photon pressure pushing things out, like electric repulsion basically, and gravity pulling it in. And at the very early times when the cosmic microwave background was emitted, we actually saw evidence of pressure waves in the primordial plasma, which is pretty cool. The universe sang in its own way. And so this is kind of a cartoon of one of those, where there's a dark matter well, where there's like a lot of dark matter creating a gravitational potential, and a lot of baryons also would have fallen into that well. And so kind of the height here is the dark matter density. Oh, I think I may have gotten that backwards, but hopefully the point is clear. And the intensity of the radiation that came out in the CMB is related to how many, what's going on in those potential wells. And so that's why you see the hot and cold spots, because it was related to how much matter was where, and like what were the amplitude of those fluctuations. And your question was about, if you start turning the knob of how much dark matter there is relative to baryonic matter, you could maybe imagine that those oscillations would just be a little different. Yeah. Okay, great question. So in general, we can learn a bunch of stuff about the early universe by using, in this kind of analogy where you have like a flashlight in a dark room shining across, maybe there's like some dust in the air or something, and you're over on the other side of the room trying to figure out things. You can learn about the flashlight because it's just shining at you, and that's how you would learn about the early universe. You can also learn about the dark room, like what's that dust that's floating around, because the light gets scattered in the universe. It actually gets gravitationally lensed around large, massive cosmic structures. And those are two main ways in which we can extract a lot of cool science from the universe. It literally is a backlight to everything that's ever happened. And it turns out a lot has happened. Oh, thank you. I'm gonna, that's 20 minutes already. Okay. Let me just tell you about these maps a little bit, and then hand it off to my colleague, Clara. So one way that we extract information from these maps is by making what we call power spectra. So I hope let me know if this gets too technical, or if you want to stop and like say, hey, John, that doesn't make sense. The thing we're plotting here is a power spectra. It's got a fancy title, just power spectra. On the x-axis is the multipole number, but more, I think it's easier to think about in terms of the angular scale on the sky. So on the right is really small scales. On the left is really big scales. And basically what you do, so if you take a map, this is a map measured by some of our colleagues in one of these telescopes in Chile. Basically take a bunch of pairs of points and imagine taking every possible pair. And you actually, is there any particular relationship that you can see by eye across each of these pairs? I claim no. And in fact, that corresponds to a trough, because there's not really anything special going on at that pair separation. But now if you squint, you can kind of imagine like, hey, like the hot and cold spots are sort of like half of a tick mark away. Maybe these numbers are a little small. And if you do the same thing where you take every pair that's like a degree or so away, averages all together, you're like, hey, yeah, there's kind of a lot going on in the math there. And that corresponds to a peak. And these are telling you, again, about those oscillations in the primordial plasma. And by doing this at a whole bunch of different separations, you could get this whole power spectra. And this is one of the things that we love to measure, because theories predict, not necessarily will that spot be hot or that spot be cold, but they predict these correlations, these statistics. And that's how we extract a lot of physics theories from them. And in fact, light doesn't have just intensity, it also has polarization. So if you also have ever taken a physics class in like high school or something, you may remember that light is actually electromagnetic waves. So there's an oscillating electric field and an oscillating magnetic field. And actually the alignment of those fields is the polarization. They can be this way, like that, or the other way. You get the idea. And there's 2 degrees of freedom because there's X and Y. And so we have 2 more power spectra to measure, which makes us very happy. And let me just say, lastly, that the theories of physics predict that these curves can deviate quite a bit. There's only one curve plotted here. And you can see that a lot of these data points are, they're pretty small and they're like kind of tracing out the curve really well at these large, high amplitude variations. But the low amplitude, very faint things, the error bars on these points are really big. So we have a lot of work to do. And we think we can extract a lot of physics. And in particular, this CMB S4 experiment that the little gray bars correspond to, that's how well we think we can do in terms of the error bars. And so we think we can kind of blow previous measurements out of the water. I'm probably out of time to give any specific science cases, but
So
yes.
fundamental question, you're looking at correlation, but if the correlation, you're asking at a certain distance, how often are the ends of that distance the same temperature? Is that what what is the correlation?
It could be positive or negative. It could be how often are they the same temperature or how often are they opposite.
Okay,
yeah.
so any non-randomness.
Yeah. And so I believe, let's see, so we're plotting this on a log scale.
You call it correlation. I'm just trying to get, you showed the distance and the ends and said, how are these correlated? So I'm wondering, is it the correlation is there similar temperatures or they're anti-correlated, they're different temperatures at this on the average at that distance?
So technically we're taking the product of them and then squaring it. So it's really like an absolute value. So if they're positive, yes, of those 2 points. So if they're both hot or both cold, that would tell you something. But if one is hot and one is cold, like that, if they oscillate like this, that's one thing. If they oscillate like this together, that's another thing. And those are both captured here. And both are interesting.
I thought you couldn't see the CMBs from land-based telescopes.
Oh, no, we definitely can.
You can't.
Yeah, so this is a perfect segue because Clara is going to talk all about the measurement realities. So let me skip a couple of slides that we don't have time for. And leave it at that. Yeah.
So hi everyone, I'm Clara. I also work at the lab with John, and so I'm going to continue the presentation by telling you a little bit more about the practicality of making these measurements and how, like, what kind of telescopes do we build and how do we manage to make successful measurements of the CMB to make all the cool science that John was talking about. So starting from what John was saying, what we are basically trying to measure is the temperature of the sky. So John said earlier that when the CMB was emitted, it was very, very hot. So the bottom axis here is like a temperature line. And so when the CMB was emitted, it was very, very hot. So we were roughly here in temperature, like 10,000 degrees Celsius. But now, because of expansion and everything is cooling down, the temperature of the CMB, when we look at the sky, it is very cold. It is about like 1 degree Kelvin or minus 272 degrees Celsius. And so this different temperature, they correspond to different wavelengths of the light. So the visible light, the light that we can see with our eyes that everything around us is emitting, is around, I'm too short. It's around here where you have the colors, right? The green and the blue and the yellow and everything. So the wavelengths of this light is in the scale of like a few hundred nanometers. So the oscillations of the light wave is a few hundred nanometers. And that corresponds to a certain temperature.
And the light of the CMB today, because it's very cold, it's not in the visible light, like we cannot see it with our eyes, but it is in what we call the far infrared or the microwave, because the size of the oscillation of this light wave, they are like a few millimeter long. So instead of oscillating very, very closely together like this for the visible light, it's more like spread up, just like the top axis is showing here. So what we're trying to do here is, you can think about it in two different ways, but they are the same thing. We're either trying to measure a light that has a different wavelength than the light that we can see with our eye, or you're just trying to measure the temperature of the sky. And so to do that, we cannot use the same kind of detectors that you would have in a standard telescope, because in an optical telescope, the detectors, like they're the same as you have in your like phone camera, for example. They're like CCD detectors, and they're sensible to visible light, but they're not sensible to microwave light. So we have to have special kinds of detectors that are sensitive to this part of the electromagnetic spectrum. And this is what is shown on that part of the slide here. We have very specific detectors that we call bolometers that are sensitive to that type of radiation. And they work very differently from the CCD that you have in a standard phone camera, but they achieve the same purpose. They're sensitive to like a specific type of light coming from the sky, and they allow us to see that type of light. And the way they work is that basically we have a mass that is at like a thermal mass that is at a certain temperature. And when this mass is hit by a photon coming from the sky, it will change in temperature, and we can detect this change in temperature because the electrical property of the thermal mass is going to change. So this is how we detect in practice the change of temperatures coming from the sky. So this is kind of what is at the core of a CMB telescope. We're trying to detect the changes of temperature coming from the sky using this very specific kind of detector. And so someone was asking earlier, wait, can we actually do this from Earth? So yes, we can, but we have to go somewhere where we can see through the atmosphere. So the atmosphere is transparent to visible light. It's why we're able to see each other, because if the atmosphere was opaque to visible light, we couldn't see each other, which wouldn't be very convenient. And there are places on Earth where the atmosphere, because it is very dry, and also because you can go very high in altitude, so you're not looking through a lot of atmosphere before you reach like the space. There are a few places on Earth that you can go where it is possible to see very well the signal of the CMB. And so there are a few places that are shown on this map, and today we'll like focus on two different places where people have been going for a few decades now to make measurements of the CMB, which are the South Pole in Antarctica and the Atacama Desert in Chile. So in this map, you want to be in blue to be good. So you can see that the base place is really to be either at the South Pole or at this very specific position in Chile. And there are like other sites that are possible, but they're actually not as good. And so I'm not going to talk about them today. So yes, it is possible to see the CMB from the ground, but you have to go to very specific places. I'm going to skip this in the interest of time. So these are a few pictures from telescope at the South Pole and in Chile that John, Julian, and I have been working on. So on the top row, you have telescopes located at the South Pole, and on the bottom row, you have telescopes located in Chile. So as you can see, the telescope located in Chile, they are like in the mountains because you want to be very high because you're looking through less atmosphere. And the reason why we're going at the South Pole is because you don't always realize because it's cold and there is snow, but the South Pole is actually a very, very dry place. It never rains at the South Pole. It also never snows at the South Pole. It snows in other places in Antarctica, but it doesn't really snow at the South Pole, which means that the atmosphere is extremely dry, and so it's a very good place to make these observations. So a lot of CMB experiments are located in these two places, so either at the South Pole or in the Atacama Desert in Chile. So John and I have both been to Chile. John has been a few times and I've been once. So if you have questions about going to Chile to work on CMB telescope, we can also talk about that.
But can I ask something really quickly?
Yeah.
You said it's temperature sensor.
Yes.
Is it wavelength specific? So you're tuning it to specific wavelengths of microwaves? Or is it just responding to any microwave to make heat?
No, it is wavelength specific, and we have to choose the wavelength specifically. It's actually the slide that I skipped. We choose the wavelength specifically to look through regions like in frequency, through regions in the atmosphere when the atmosphere is specifically transparent, because even in these regions, so here, if you're at 1, it means the atmosphere is transparent, and if you're at 0, the atmosphere is opaque. And so you want to be in frequency in the regions where the atmosphere is transparent. So we tune our detectors and our telescope and all of our optics to be in this region. And the frequency that are above like 350 here, it's not shown on the plot, but the atmospheric transparency really degrades. And so you cannot observe at this frequency from the ground, you have to go to space. We are building, there are two kinds of telescopes that we are building, depending on the science goal that we want to achieve. So John didn't have time to talk about the details of this, but I'm still going to show them some pictures of the different type of telescope that we build. I'm not going to go into the details, but just the basic idea is that we build these two different telescope architecture to see different features of the CMB. One type of telescope is going to allow us to observe like very wide part of the sky, but not very deep, so not very precise, but with a very good angular resolution. Whereas another type of telescope is going to allow us to focus on a small patch and really have like extremely good sensitivity. And you don't build the same type of telescope for that. So the first type of telescope is a large aperture telescope, and they're really very large, like you can fit people inside of the receiver. And then the receiver itself goes into the mount. And so you have people here giving you an idea of the scale of this thing. And so there is currently one telescope like this located in Chile, which just achieved commissioning and has started to take observation. And in the context of CMBS4, so this experiment that we're working on, we're going to build 3 or 4 more telescopes like this one to make observations from Chile. And then these are pictures of small aperture telescopes, so much smaller. This is basically the size of a person. And so this is showing one of these telescopes observing from Chile and 4 of these telescopes observing from the South Pole. And so the telescope is, so the optics tube that you're seeing here is kind of, it's here in the mount. And then the big part that you see above, like the kind of scoop or like the aluminum tubes that you see on the top picture, they're not actually the telescope itself, but they're here to shield the telescope from the light coming from the ground and from other part of the sky. Because we're trying to make a measurement that is extremely precise. And so you don't want to have any stray light coming from like the ground itself or from other part of the sky that you're not currently directly looking at. And so a lot of what you're seeing on the picture is actually shielding to protect the telescope and the very sensitive optics from like stray light coming from the ground or from other part of the sky. And so you don't actually directly see the optics tube on these pictures, but you're mostly seeing actually the shielding. And so this is a picture that shows you how exactly it's done. So the optics tube is where it says biceps 3 cryostat, and then on top of it you have the probe baffle and the ground shield, and all of this is shielding. But really the telescope, like the receiver itself, is this tube here. And so now I am going to kind of take you through the different elements that compose one of these receivers. And we have brought like some samples here of these different elements that I am going to pass around. So you are free to like touch them and look at them. So this one, I'm just saying this before we start, it's kind of heavy, just like don't shake the box or try to like flip it, just keep it upright. And the rest of it should be fine to pass around, but please be careful with this thing. So starting from the top, we have a vacuum window because all of our telescopes are under vacuum because what we're trying to measure is a signal that is very, very cold. It's only like a few Kelvin above absolute zero. And so if you want to measure that signal, you don't want your telescope itself to emit radiation that it would detect and that it would prevent you from detecting the signal from the sky. So the telescope itself needs to be colder than what you're trying to measure. And to achieve this, we need a very advanced cryogenic system, and we need everything to be under vacuum, which is why from the top, we start with a vacuum window to keep everything under vacuum. And the amazing thing is that you would think that to keep a system like this one under vacuum, you need something very strong and heavy. But our colleagues at Harvard University have developed this material that I'm going to pass around. And this thing, so of course it's not full size, but these little things, it can hold vacuum for an entire telescope. And it's pretty amazing if you think about it. It's just like a few sheets of plastic. So of course it's a specific type of plastic, and it's reinforced with like the same thing that people use for Kevlar. But this can hold vacuum for an entire telescope. So I'm going to pass it around, but if you think about it, it's pretty amazing. So this is the vacuum window. And then after the vacuum window, it's a telescope. So you need an optical system. So you need optics, and in particular, you need lenses to focus the light that's coming from the sky before it reaches your detectors, your bolometers that I was talking about earlier.
And that plastic is transparent to the light.
Yes, exactly. So this is an example of lens that we use in our telescope. Again, not full scale. In reality, these tubes are about 50 centimeter in diameter, right? So like this. And so you could think, wait, this is completely opaque. Like, how can this act as a lens? But again, we are not observing visible light. We're observing microwave. And so this is transparent to microwave. It's not transparent to visible light, but it works exactly as a lens in a regular telescope, but for microwave. And so this, again, is made of plastics. Some of them are made of a special kind of ceramic, but plastics works really well as well. And then once the light has been focused, it reaches the focal plane where the detectors are. So the detectors are the bolometers that I was talking about earlier. And so here we have a detector wafer. So this is, I don't know how many, a few hundred bolometers, something like that.
Probably 1,000 or 2,000.
1 or 2,000? Okay. Do you know which frequency it is? Anyway, so typically in a telescope, you would have around 12 tiles like this one to make like the entire array of detectors. And so these are the equivalent in your phone camera. This would be like CCD detectors, but for us, these are the bolometers. So this is really the sensitive part of the experiment. This is what is going to receive the signal from the sky and turn it into something that we can measure. And so these bolometers, so this is just the detectors, but we mount them into like what we call a module. And so it's an assembly of like the detectors themselves, but also some readout electronics and some like additional optics. and we package everything and then we put it on the focal plane. And so this is the thing that you should not shake. This is like a detector wafer that would like integrate the detectors themselves and some readout and some filtering and everything.
So would you call this a refractor?
Yes, it is.
What's a spatial, is that a set of receivers, the little wafer, or is it the whole wafer the receiver?
So the wafer, we take like, we put about like 12 wafer in one receiver.
In terms of spatial resolution, are the little bits of can you distinguish the microwaves over that wafer in different places?
Yeah, so each detectors receive a signal and then it kind of paints like a picture on the sky, like each sees like a different part of the sky, and then we can reconstruct a map. I will show example of that in a minute. And the last thing that I have here, if I manage to open it. So these are electronic chips that are used to read out the detectors. So I'm not going to talk about this because we don't really have time. But once you get the signal from the sky and you want to pass it out to your like detection system and like get the data, you need to transmit it like in an electrical way. And so we built like advanced readout system to like kind of transcribe the signal that the detector sees into like an electrical signal and then get into like a computer. And these chips are used as part of this system. All right, so these are just like some pictures of how it is in reality. So this is showing like a full size lens and an optical filter. This is showing like all of the wafers assembled. So these wafers are square. The one I'm passing around is hexagonal, but it's exactly the same thing. And this is showing like all of the electrical connections that you have to make for this to work. And so you can imagine that you better have a good mapping of which wire goes where if you want to be able to make nice maps. Speaking about making a map, just before I conclude, this is what our data look like. So we're not taking like pretty pictures of the sky where you can see stars and everything, because our detectors are sensitive to change in temperature. So as the telescope is like scanning the sky like this, so this is the movement that's shown on the top, the detector, they see variations in temperature like this. So if we sum the signal of two detectors, we get the temperature. If we take the different signal, we take the polarization. Don't really have time to go into the details of how we do like temperature and polarization, but I can answer a question after that. And then we take this polarization signal, so these little like squiggles, and this is what we're going to turn into maps of the sky that John was showing earlier. And so for one little squiggle like this, so this is the equivalent of about 50 minutes of observation. So this is the full sky map of earlier. We're going to zoom on that patch at the bottom. And so if we observe the sky for 15 minutes with one detector, we can map out just like a tiny band like this. Then if we observe the sky for 5 hours, this band gets a little bit bigger because the sky is moving. So if we keep moving the detector, the telescope, and the sky is moving above us, we see more of the sky. And then we rotate the telescope on itself to see different parts of the sky. And so we start piecing out like more of the sky. And then we continue doing that for an entire year. And so one detector for an entire year is going to see all of this part of the sky. But then we have thousands of detectors in the focal plane. And so we add everything together. And this is how we get these maps of the CMB for a small part of the sky. And if you want to do that on the full sky, you would have to repeat this on every little patch of the sky. And I think that's it for me. Yes. So I'm going to pass it over to Julien, who is going to tell you a little bit how it is to actually take this raw data and make map, because I just showed you like pretty pictures, but Julien is a graduate student working on the experiment, and he's actually doing the hard work of turning these squiggles into nice maps. So go ahead, Julien.
You ever see a telescope on a satellite in the future?
So there have been telescopes on satellites. You may have heard of COBE and WMAP and Planck. And there are projects for telescopes in space. But so none of us is working on any of these projects. And these projects are somewhat uncertain. But yes, there are projects, because going to space is more expensive and you have to build like a really strong telescope, but it has some advantages.
Actually, I'm working on one of the
You
projects.
worked on, you worked on
but-
Pico,
Yeah,
sorry.
it's quite uncertain, as you said. So yeah, that's a great introduction. I think in the interest of time, I'll try to keep that reason like within time limits. So John, Clara, and Juliet came to me and asked me if I could just talk about what it's like doing science. So I'm not going to show any too technical details or like any frightening equations or so forth. So just gonna babble about my life. So yeah, so I'm a visiting PhD student. I did my undergrad in France at École Polytechnique, and I specialize in physics. Then I went on doing my master in high energy physics at ETH in Zurich, Switzerland, and so I'm not a UC Berkeley student, but I'm a French PhD student, but I'm visiting here for the extent of my PhD. So I'm hosted at Berkeley Lab. So it's a great experience working at lab. So what is it like doing a PhD in cosmology? First of all, I want to clarify a few things. I'm not a theoretical physicist. So that means I don't really do phenomenology, but like the why and how of the CMB. I'm not really doing any of that. I'm not an instrumentalist either, so I don't do anything that Clara does, at least not for now. I'd love to do some of that, but that's not what I'm doing currently. So what do I do? And I'm still figuring it out myself. So yeah, Clara gave it a bit away. I'm doing computational cosmology. So what the heck does that mean? Well, I'm mostly working with data simulations. So I make simulations of what would be telescope would be observing. So typically that looks like the raw data that Clara was just showing you a bit earlier on. So I make simulations of like somewhat realistic data. I run them through big pipelines of data analysis, and I try to see if it all makes sense. And most of the time, it doesn't. So most of my job is making sure it eventually converges and that it's actually making sense in the end. So what's a typical day in the life of a PhD student? I do a lot of coding and I read a lot of documentation of diverse Python packages. I'm just going to mention one of the software I'm using for making data simulation that has been developed here at Berkeley Lab.
Can I ask, do people give you what they want you to simulate? And you have to figure it out, because the simulation means you're making certain assumptions.
Yeah.
When the assumptions are right, this is what you should get.
Well, we have models of
Are you figuring out what assumptions you want to play with to see how you can match what you actually observe?
well, actually a bit of both. Like there are already existing models of like say atmospheric contamination. So we have like already implemented models, but part of my job is also to build on that and like adding other like subtleties and layers to these already existing models. So I'm not building anything from scratch, but I'm building on things.
So you're working on removing artifacts from the data?
Yeah, in some way, like if part of what Clara has been mentioning is well, we want to go to places where there's not so many atmosphere, and part of my job is what if you have like a remaining contamination coming from instrumental systematics or like some remnants of atmosphere? How do you mitigate that through your pipeline? So yeah, I'm modeling all that. I'm taking that into account in my data model. And yeah, so basically also I have my PI also guides me through what I need to analyze and whatnot, but I'm building on top of that as well. Yeah, I saw
I
a
have a
question.
question about Python. Is that pretty much the standard in all, and it's like, that's all they use these days in a lot of sciences, especially, something like this. Is that
Okay.
basically it these days?
Okay, I'm gonna give a not very satisfying answer. I know Python, I don't know C. That's but honest, no. Python is very nice because it's very easy to manipulate and it's very practical for making like notebooks to share with the community and
It's like everybody's using Python in just about every field. Must be something easier to learn than like C or
well,
C.
it's
I
definitely
used C++ a long time ago. It was very difficult.
yeah. I think it's
So
definitely much easier and well, some of the low level code is probably still written in C, but you have like a ton of wrappers these days to
Right, right.
to
A lot of
translate.
libraries that you
Yeah.
can just pick and
Yeah.
choose and things like that.
So yeah,
One question. I mean, you will do a lot of signal processing, I believe, daily,
yeah.
day in, day out. So why don't you use MATLAB or Simulink, such kind of tool to
Wednesday.
seem to be more natural in your field? Which specific library do you think is more useful for you to use Python and that?
I don't know. I don't really like MATLAB. I mean, I think MATLAB was probably more. I mean, some people still to these days are still using MATLAB within the collaboration, but I think we can do a lot of data analysis these days with Python, and it's more convenient for people. So I don't have a very strong argument. I would say just that like people just are more comfortable with Python these days. That's
Which specific library do you
just
use
like
to-
the
Is there any
AstroPy,
specific library about astrophysics, that kind of thing?
PyPy, a bunch, AstroPy, and then all the classical NumPy, JAX. So
Yeah.
if yeah, and we want to, because we're also processing a huge amount of simulations, we want to parallelize as well, and so using like OpenMP, MPI for Pi, things like that. Yeah. How much time do I have left? Like in 30 seconds. Okay, I have a bunch of unread PDFs that I have downloaded and that I still have to read. So that's like basically I want to keep up to date to the latest results in cosmology and in CMB. And so lately we have had a ton of results coming from different collaborations. So I have to catch up on that. And also I wanted to highlight that part of the job is also to meet with other people. You don't just stay in your own office and you can't really do things on your own. Part of the collab, we are part of a collaboration which has I don't know how many people within it, but it's like a huge collaborations, and so you have to communicate a lot. So part of the job is also to attend the meetings and meet with colleagues and advisor and share ideas, because it's cosmology has really come to precision science. So now you have really to like communicate with the state-of-the-art experts in the field. So yeah, you just don't do that on your own these days. And I drink a lot of coffee, but and just in short, I just want to highlight that what part of the things that keeps me motivated is that CMB is a somewhat very simple theoretical framework, but it would lead to profound implications for fundamental physics. And that's me. And this is a software I use. It's called TOAS for time-ordered astrophysical scalable tools. And just a fancy word to say that I'm making simulations of raw time-ordered data. So the data that you will be actually measuring from your telescope by scanning, by scanning with your telescope. And so it has a bunch of wrappers also to and bunch of methods to make maps out of the raw data. And yeah, that's me. And I like to take photos, I guess, and yeah, and make seeing images. ChatGPT.
Do you want
So what's the funding status of your, does Elon Musk?
I think we're good for like 10 minutes of questions.
to? Yeah, we can.
It's. I think I'm good for now. Hopefully, yeah. I'm in my first year, so I don't want to think too much about it.
Maybe your friend.
Yeah.
The other question here, so it's related to Elon Musk. So they have so many Starlink satellites. Will that affect your observation? Do you need a way to filter out those very bright things? First question, and the second question is: even though you are very high above the ground, above the sea level, you still have some atmosphere around you. Some air would have background radiation, will have ionosphere around the Earth. How do you filter out some kind of background noise? Even though you cool your telescope, but you still have the signal around you.
You want to take these one on one?
I can take the question on atmosphere.
Okay. Well, so we actually, to start with your first one, then, we wrote an entire paper about what we think the influence of satellite constellations will be on our future data sets. It kind of depends a little bit on how they engineer these things. There have been some instances of successful communication where they've kind of like blackened the size or, made their antennas more directional or something like that. I am not aware of any current CMB experiments being crippled by this, but I think we're annoyed for sure. I don't know if you guys would paint that as I don't believe we think that it's going to ruin our field, but I think we would prefer that they weren't there.
Yeah, and I know that there are communications with the I don't remember the name, but like the board that regulates frequency attribution in the United States, to make sure that the bands in which we observe also stay protected from this like satellite communication, not just like the visual like pollution, but just also like the fact that they're emitting in certain bands. And so we are trying to engage with this like regulatory people to make sure that we can still do our science. So it's not as John said, we're not crippled by it for now, but it is certainly a concern for the future, and we kind of have to keep an eye on it to make sure it doesn't become limiting.
But for what it's worth, they are pretty easy to find and identify in the data. We know it's not part of the cosmic microwave background because it is really glaring obvious. So you can cut that part out when you see it. The only problem is if it makes you cut out too much.
You want to talk about the atmospheric question?
But you work on that, so maybe you want to say something about it?
Yeah, so it's actually a very good question. And you have many ways of mitigating, like just on the topic of atmosphere. Like one thing would be to just simply filter like filter some of the signal at the scale because the atmosphere is moving at a certain scale, and so it's extending on a certain scale. So in your data, you can try to like remove some of these scales. So you'll be actually losing some of the signal, but it's happening on scales where it's still acceptable for us to kind of filter this out. But I'm also exploring other ways of not being so aggressive with the filtering. And one of the ideas that I have in mind and I'm exploring is like using the fact that the atmospheric emission is different at different frequencies. And so kind of because we have different frequency channel, we can try to make a model of the atmosphere at different frequency and subtract it from our time order data. But it's very much a concern how to efficiently remove that all these contamination without affecting our signal too much. Like
one small thing.
Yeah.
Another trick that you can play sometimes is if you're trying to measure the polarization of the light, but you don't necessarily care about the intensity, which oftentimes is your goal. You can take, and then the other fact is that the emission from the atmosphere, the thermal emission, the radiation that it emits, is primarily unpolarized. So what you can do is you can insert what we call a birefringent material and spin it fast in front of your telescope, a rotating half-wave plate is the term we use. And that takes your polarization signal and moves it to a higher frequency, kind of like AM radio takes your kilohertz voice and moves it up to megahertz so it can travel across the ionosphere, away from the kind of dirty region where the atmospheric noise is moving. So not every telescope does that, but some do, and it can work well.
Can you use the same trick that astronomers use with light? That is, you can beam microwaves up to see what the atmosphere is doing to the wavelength you want to measure and measure reflection.
Oh, like use a LiDAR or something?
Well, no, the light astronomy, they measure the turbulence in the atmosphere by sending a laser beam up, and then they adjust their mirrors and so forth to compensate for what that laser beam tells them the atmosphere is doing. And I'm just wondering if there's any possibility of using that at a microwave level, the same kind of thing to filter, to get out the atmospheric.
He's talking about adaptive optics.
Yeah.
So
Go ahead.
Okay. So a fun fact about our telescopes is the angular resolution of our telescopes is not limited by the atmosphere. A lot of other telescopes, you may hear them talking about the seeing, how many arc seconds can they get, and what mountain are they on top of? That doesn't matter at all for us. It is the size of the entrance pupil of our telescope, which can be the first mirror, which might be a few meters, or the first, basically the first lens, which might be about yay big. And so we're in the nice friendly regime of being diffraction limited, if you're familiar with that term. But if not, it means that the atmosphere doesn't distort our beams. It does add noise. And so funnily enough, actually, a few of us have put in a funding proposal this year to do exactly that, not to measure the distortion of the beam and correct for it, but to be able to measure the noise that it adds and subtract it. So we'll see. It hasn't been proven yet, but there are promising signs.
I think we also have a funding proposal, but with scenarios with the LiDAR.
Yes, so
Same.
yeah,
That's the same thing.
Yeah.
well, we put in a few funding proposals. I'm on one of them.
Yeah, I'm on a different one.
It's going to come kind of out of the blue. We're talking about dark energy and dark energy before. And one of the projected, say, ends of our universe is sort of a cold death, right? Sometime. What if, we don't know where the Big Bang came from, how it was caused, okay? What if, what we're seeing, maybe there was our Big Bang sort of exploded and overrode an old dead universe. Maybe this is almost kind of a cyclic thing, and if we're seeing, the things the dark energy and dark matter we can't see,
is stuff from a previous universe. Have there been any simulations to try to figure out if something like that happens? That might be, what we'll see. It could happen cyclically. The universe is born, grows up, dies, another one, basically, and you assume all this, the dead universes beneath it.
So I think the jargon word for the models that you're talking about, we often call ekpyrotic models.
Okay.
And let's see. So there are theories that they're not fully self-consistent yet, but it may be that we just haven't done enough like clever mathematics that can potentially describe aspects of our universe, but not all of them, with a bouncing cosmology. It turns out that math is really hard when you have to bounce through a singularity, general relativity, everything becomes infinity, and quantum effects probably really matter. And so it's a little bit of an open question. But that being said, through specifically the measurements of the cosmic microwave background, we have a really good idea of the basically the seeds that seeded cosmic structure that have gravitationally collapsed to become the galaxies and whatnot that we see today. And they follow a very specific pattern. It's a nearly scale-free, slightly red power spectrum, to use the jargon term, but basically it means that bigger fluctuations in like physical size are a little taller, like more dense, and ones that are smaller in physical size are a little bit less dense. So that's the red power spectrum. And I believe that whenever people have tried to write down theories of physics and crunch through the general relativity and the quantum mechanics, it's pretty hard to get that kind of power spectrum. I think they generally predict blue power spectra. One of my colleagues can correct me if I'm missing their favorite theoretical model that they know of. And so, I can't say for sure, but if you said I had to put $20 on which one is true, I'd say it's probably we have an inflationary universe instead of an ekpyrotic one, where the inflationary one is basically it just kind of went bang once, as far as we know. There's a couple other lines of evidence that we could really get into the weeds of, but that probably will take a little bit longer.
Well, I think for now, that's the time that we have. So let's thank our speakers again.